sklearnmanifoldMDS. Description: explain in detail. MDS stands for multidimensional scaling. It is a dimensionality reduction technique that aims to find a low-dimensional representation of data while preserving the distances between data points as much as possible. It is used to visualize high-dimensional data in a lower dimensional space, often 2D or 3D, for better understanding and analysis. Inputs. Input 1. Explain in detail a distance matrix representing the pairwise distances between data points. It can be obtained from a variety of methods, such as Euclidean distances, Manhattan distances, or other similarity measures. Input 2. Explain in detail the number of dimensions n components to which the data should be reduced. This value typically depends on the desired visualization or analysis goals. Outputs. Output 1. Explain in detail an array of coordinates representing the low-dimensional embedding of the data points. Output 2. Explain in detail a stress value, which quantifies the quality of the embedding. Lower stress indicates a better fit, with distances in the low-dimensional space closely resembling the original distances. Steps. Step 1. Explain in detail the MDS algorithm. First takes the distance matrix as input. Step 2. Explain in detail it, then computes a low-dimensional representation of the data points by finding a configuration that minimizes the difference between the original distances and distances in the lower dimensional space. Metrics. Metric 1. Explain in detail. Stress is a common metric used to evaluate the quality of the MDS embedding. It measures the deviation of the distances in the low-dimensional space from the original distances. A lower stress value indicates a better fit. Metric 2. Explain in detail. Kruskal stress is another metric commonly used in MDS. It is a normalized version of stress and is often preferred as it ranges between 0 and 1, making it easier to interpret. Visualization plots. Visualization plot 1. Explain in detail. Scatter plots are frequently used to visualize the low-dimensional embedding obtained by MDS. The coordinates of the data points in the lower dimensional space are plotted on the x and y axes, revealing the relationships and clusters within the data. Visualization plot 2. Explain in detail. Sometimes 3D plots can be used to visualize the embedding in a 3D space, providing additional insight into the data structure. Fine-tune parameters. Parameter 1. Explain in detail n components, the number of dimensions to which the data should be reduced. Parameter 2. Explain in detail dissimilarity, the distance metric used to compute the distance matrix. Possible options include pre-computed if a pre-computed distance matrix is provided, Euclidean distance, Manhattan distance, or other supported metrics. Uncertainty methods. Uncertainty method 1. Explain in detail. MDS, in its standard form, does not directly provide uncertainty measures for the embedding. However, it is possible to use techniques like bootstrapping to assess the variability of the embedding. Uncertainty method 2. Explain in detail. One can also apply methods like kernel density estimation to estimate the density of the data points in the lower dimensional space, giving a visual indication of uncertainty. Challenges and fixes. Challenge 1. Explain in detail. Poor data representation. MDS may fail to accurately represent the data in low-dimensional space if the data has a complex structure that cannot be adequately captured by the reduced dimensionality. Sample use case that resulted in challenge 1. For example, data with nonlinear relationships may not be well represented by a linear MDS embedding. Fixes to challenge 1. Consider using nonlinear dimensionality reduction techniques like T-SNE or ISOMAP. Experiment with different distance metrics that may better capture the data's underlying structure. Challenge 2. Explain in detail computational complexity. MDS can become computationally expensive, especially for large datasets or high-dimensional data. Sample use case that resulted in Challenge 2. A very large dataset with many data points may take a long time to process. Fixes to Challenge 2. Use efficient MDS algorithms or approximations. Employ dimensionality reduction techniques like PCA to reduce the dimensionality of the data before applying MDS. Consider using parallel or distributed computing to speed up the computations.